The James Webb Space Telescope opened its eye, looked 13 billion years into the past, and saw something that should not be there. Galaxies fully grown when the universe was a newborn. Black holes too massive to exist. A cosmic chemistry that breaks every textbook. You're about to travel to a galaxy older than time should allow. A world where methane whispers of life, and a void that hides a different physics. If this fascinates you, hit subscribe. Your curiosity belongs here. Strap in. We begin. July 11th, 2022. A small team gathered around a screen at the Space Telescope Science Institute in Baltimore. They had waited decades for this moment. The first deep field image from the James Webb Space Telescope was about to load. When it finally appeared, the room went silent. What they saw was not what they expected. The image showed a patch of sky smaller than a grain of sand held at arm's length. Inside that tiny patch were thousands of galaxies. Some were close, glowing in familiar shapes. Others were impossibly far, their light stretched and reddened by the expansion of space itself. But the strange part came when astronomers began measuring the most distant ones. The galaxies near the edge of the image were too bright, too organized, too massive. According to every model of how the universe should grow, those galaxies should have been faint smudges, barely formed, still gathering their first stars. Instead, they looked like fully built cities of light, sitting in a cosmic era when only construction sites were supposed to exist. One scientist later described the feeling as watching a baby photo and seeing an adult instead. The image you may have seen on news broadcasts shows a galaxy cluster called SMACS 0723. Its gravity acts like a giant lens, bending and magnifying light from galaxies far behind it. This was supposed to help Webb peer farther than ever before. It worked. But what came back through the lens was a problem. Some of those distant galaxies appeared to be more than 13 billion years old. That is dangerously close to the age of the universe itself, which is estimated at roughly 13.8 billion years. The math left almost no room for these galaxies to form, grow, and mature. A senior astronomer told reporters that the early results had created a quiet panic. Models built over 40 years suddenly looked wrong. Predictions made in scientific papers from the previous decade no longer matched what Webb was showing. Some researchers stayed up all night running simulations, trying to recreate what they saw. The simulations failed. Then came the second wave of shock. Webb did not just find one or two early galaxies. It found dozens, then hundreds. Each one looked more developed than it should be for its age. Some had clear shapes. Some had heavy elements like iron and oxygen, which require generations of stars to produce. Some even appeared to have central black holes already feeding on surrounding gas. This was not a small adjustment to the cosmic timeline. This was a crack in the foundation of modern cosmology. Inside private meetings, the question was no longer whether the standard model needed updating. The question became how badly it was broken. Several teams began openly discussing whether the universe might be older than 13.8 billion years. Others suggested that early star formation must have been hundreds of times faster than anyone believed possible. Neither option felt comfortable, and the deeper Webb looked, the worse the picture became. Each new image, each new analysis, returned the same impossible signal. Galaxies were not behaving the way they should. Time itself appeared to be telling a different story than the one we had written. Then Webb turned its mirror towards something that would shake the field even harder. In the standard story of the universe, the first 500 million years are a slow, dim, gentle chapter. Tiny clumps of gas slowly come together. Faint stars flicker on. Galaxies are still gathering, like sand grains pulled into early mounds. By textbook logic, this era should look quiet and primitive. Webb saw the opposite. When the telescope pointed toward the faintest, most ancient pinpricks of light, it found galaxies that were already burning bright, not embers, full furnaces. Some of them shone with the intensity of hundreds of billions of suns combined. The light reaching Webb's mirror had traveled for over 13 billion years, which means we are seeing these galaxies as they existed when the universe was barely a toddler. That fact alone should not be possible. Standard models predict that during this era, only small, messy proto-galaxies could form. They should look like cosmic blobs in the middle of construction. Random, dim, simple. Webb instead found galaxies that already had structure, density, and shocking amounts of mass packed into small spaces. A team at the University of Texas led one of the early surveys. They measured the brightness, distance, and stellar content of these very young galaxies. The results came back so unusual that the researchers double-checked the data multiple times. They wanted to be sure they were not making a mistake. The numbers held. Some of these galaxies appeared to contain tens of billions of solar masses worth of stars. To put that in perspective, that is roughly the size of a fully mature galaxy in today's universe. Yet Webb was seeing them as they were when the cosmos had barely cooled enough to allow stars at all. It was like finding a fully grown oak tree 5 minutes after a forest fire. The implications spread through the scientific community quickly. If these galaxies are real, and if their masses are correct, then either stars formed faster than physics allows, or the universe is older than our timelines suggest, or some unknown ingredient powered an explosion of cosmic growth in the first 500 million years. Each option carries serious consequences. Faster star formation would require physical conditions that current chemistry cannot easily produce. An older universe would force changes to the entire timeline of cosmic history, including the cooling of the first hydrogen and the moment of recombination. An unknown ingredient would mean that something fundamental about gravity, dark matter, or early energy is missing from our equations. Some scientists tried to find errors. They suggested measurement issues, dust contamination, or instrumental glitches. But Webb's instruments are extremely precise, and follow-up observations confirmed the original readings. The galaxies are there. The light is real. The mass is real. One researcher described the situation as an alarm bell ringing from the dawn of time. It became clear that Webb was not just adjusting a few details, it was forcing astronomers to reconsider the very concept of cosmic infancy. The early universe, as Webb sees it, was loud, fast, and aggressive. It was building galaxies at speeds that should not be possible. This raised a quiet but uncomfortable question inside the field. If our understanding of the youngest cosmos is wrong, what else might be wrong? The next discoveries would push that question even further, beginning with a class of galaxies that broke the system completely. In early 2023, a team of astronomers, led by researcher Ivo Labbé, published a paper that quietly detonated inside the field of cosmology. They had analyzed Webb data and found 6 galaxies that should not exist. The team gave them an unofficial nickname that spread quickly through the community. They called them universe breakers. The reason was simple. These 6 galaxies were enormous, far too enormous. They appeared in a cosmic era when the universe was only about 500 to 700 million years old. According to standard physics, the largest galaxies of that period should contain the equivalent of a few billion solar masses. The universe breakers contained tens of billions, with some estimates pushing past 100 billion. That is the mass of the Milky Way today, packed into something that should still be a cosmic infant. Imagine finding a fully grown elephant inside an egg. The math became uncomfortable for everyone. To produce that much stellar mass in such a short time, gas would have needed to convert into stars, with almost perfect efficiency, almost no waste, almost no leftover material. Real galaxies do not behave this way. Star formation is messy, slow, and inefficient. Most gas is lost to radiation, ejection, or heat. The early universe should have been even messier, not more efficient. Yet the data refused to lie. Some critics tried to explain the universe breakers as something else. Could they be supermassive black holes glowing brightly and tricking the instruments? Could they be galaxies sitting in front of even older galaxies, blending their light? Could there be measurement errors in distance? Each idea was tested. Each idea was challenged, and while a few of the 6 galaxies did turn out to have unusual properties that softened the problem slightly, several remained stubbornly impossible. One of them, in particular, became famous. It contained roughly the same number of stars as the Milky Way, but it existed when the universe was only 5% of its current age. There is no clean way to explain that with current physics. The name universe breakers stuck because the implications truly threaten the standard model. If even one of these galaxies is real, then early cosmic growth must operate under rules we have not discovered. Some scientists openly suggested that dark matter might behave differently than we thought. Others suggested that the early universe had moments of intense gravitational collapse, like cosmic boiling points, where matter clumped together in ways modern equations cannot describe. A few proposed something even stranger. They suggested that the first stars were monstrous, hundreds of times more massive than typical stars today, and that they collapsed into black holes almost instantly. Those black holes would then attract matter at extraordinary speeds, building galaxies in a fraction of the expected time. This idea is still highly debated, but it shows how desperate the search for answers has become. The universe breakers are not just curiosities, they are warnings. They tell us that something fundamental is missing from our understanding. Either the universe grew faster than physics permits, or it carried hidden ingredients we have not detected, or the timeline itself is wrong. Each option pulls at the same loose thread, and when astronomers followed that thread, they found something even more disturbing waiting in the next slice of cosmic history. If the universe breakers shook cosmology, the next discovery rattled the entire framework of how galaxies are supposed to grow up. Spiral galaxies are some of the most beautiful objects in the cosmos. The Milky Way is one, Andromeda is another. They have flat disks, sweeping arms, central bulges, and graceful rotation. They look ordered, calm, mature. For decades, astronomers believed spiral galaxies were the result of a long, slow process. Gas had to settle, stars had to gather into a disk, the disk had to cool and stabilize. Spiral arms required gravitational waves rolling through the structure for billions of years. The textbook timeline placed the first true spirals at roughly 6 to 8 billion years after the Big Bang. Anything earlier was supposed to be small, lumpy, and chaotic. Webb destroyed this assumption. When the telescope examined the early universe, it found galaxies with unmistakable spiral structure as far back as 1 to 2 billion years after the Big Bang. Some had multiple arms, some had clear central bulges. Some looked nearly identical to galaxies we see in the modern cosmos. They were not faint hints of disks, they were full disks, organized and rotating in patterns that match galaxies billions of years younger. This was supposed to be impossible. A British astrophysicist working on the data described it as finding a fully built city in what was supposed to be an empty wilderness. Other researchers said the discovery felt like watching a film reel jump forward by accident. The cosmic clock seemed misaligned. To understand why this matters, picture how a galaxy is built in the standard model. Gas falls inward, random clouds collide, energetic explosions disturb the structure. The whole environment is violent. It should take many cosmic generations before that chaos calms enough to form a stable disk. A spiral disk is even harder. The arms require a smoothly rotating structure where gas and stars can ripple together in long, predictable patterns. To form spirals so early, the universe would need to be far calmer, far quicker, and far better behaved than it should have been. Webb's data shows that galaxies were not following the slow construction blueprint. They were settling into mature shapes within a fraction of the time previously believed. Some teams found that nearly half of the galaxies in the early universe show some kind of disk structure. That number should be near zero, according to traditional simulations. There are several theories trying to explain this. One suggests that early dark matter halos, the invisible scaffolding around galaxies, may have formed faster than expected. Another suggests that early gas was denser and cooler, which would speed up disk formation. A third proposes that small mergers between mini-galaxies stabilized into disks much earlier than predicted. None of these ideas fully solve the mystery. The deeper concern is that the universe seems to have been building structure with surprising precision. Order from chaos appeared too quickly. The physics of spiral formation may need to be rewritten. This kind of mature structure suggests something even more unsettling. If galaxies stabilized this fast, then perhaps the early universe was running on a clock that did not match our equations. And if the cosmic clock itself is wrong, then the next puzzle becomes deeply troubling. Two different methods of measuring the universe's age are giving two different answers. One of the strangest and most stubborn problems in astronomy has a calm, clinical name, the Hubble tension. But behind that name sits a quiet crisis that grows worse every year. It is the discovery that the universe seems to be expanding at two different speeds, depending on how you measure it. That should not be possible. The expansion rate of the universe is called the Hubble constant. It tells us how fast galaxies are flying apart from each other. This number determines the age, size, and ultimate fate of the cosmos. For decades, astronomers have tried to pin it down with as much precision as possible. They use two main methods. The first method examines the cosmic microwave background. This is the faint glow left over from the Big Bang, captured in extreme detail by satellites like Planck. By studying the patterns in this ancient light, scientists can calculate how fast the universe should be expanding today. The second method uses objects in the modern cosmos. Astronomers measure stars called Cepheid variables, which pulse with predictable rhythms. They also use Type 1a supernovae, which explode with consistent brightness. By combining these two ladders of distance, they directly measure how fast nearby galaxies are moving. Both methods are extremely accurate. Both methods have been refined for years. Both methods should produce the same answer. They do not. The cosmic microwave background gives a Hubble constant of about 67 kilometers per second per megaparsec. The local measurements give about 73. The difference may sound small, but in cosmology, it is a chasm. The universe cannot have two expansion rates, yet the data refuses to budge. For years, scientists assumed the discrepancy would shrink as instruments improved. Instead, the gap grew. New measurements only made the disagreement sharper. Some hoped the James Webb Space Telescope would solve the problem by providing the cleanest, most accurate measurements of distant stars ever made. Webb did indeed deliver crisper images, but the tension remained. The local universe still appears to expand faster than the early universe predicts. This means one of three things must be true. Either our measurement of the early universe is wrong, or our measurement of the modern universe is wrong, or something is fundamentally missing from our understanding of cosmic evolution. The first two have been tested relentlessly. The third is the most uncomfortable. Some researchers propose a phenomenon called early dark energy. This would be an extra burst of unknown energy in the first few 100,000 years after the Big Bang. It would push the expansion of space slightly faster early on, then fade away. This idea would resolve the tension, but it requires inventing a new force that has never been directly detected. Others suggest that gravity itself might behave differently across cosmic distances, or that the speed of expansion changes in ways our equations do not capture. The Hubble tension is no longer a small puzzle. It is one of the strongest hints that our model of the universe is missing a deep piece. And when combined with what Webb found in the early cosmos, the picture becomes harder to ignore. The universe seems to be telling us that its growth, its age, and its structure are all slightly off from what we believed. And when astronomers turned their attention to early black holes, the contradictions became even more shocking. A supermassive black hole is one of the most extreme objects in the cosmos. It is a region of space where gravity is so concentrated that not even light can escape. The largest of these monsters contain millions or billions of times the mass of our Sunday. They sit at the centers of nearly every large galaxy, including ours. The textbook story used to be straightforward. These giants formed slowly. Smaller black holes merged. Gas fell inward. Generation after generation of accretion built up the mass. The biggest supermassive black holes were thought to require billions of years to grow. Webb shattered that idea. The telescope detected enormous black holes in galaxies that existed less than 700 million years after the Big Bang. Some of these monsters already weighed billions of solar masses. That means they were nearly the size of the supermassive black hole at the center of our own galaxy, but they existed when the universe was barely a tiny fraction of its current age. It is like discovering a fully grown whale inside a fish egg. The growth math becomes deeply troubling. Black holes can only swallow gas and stars at a certain maximum rate, set by physics itself. This limit is called the Eddington limit. It exists because the radiation released by infalling matter pushes outward, blocking new matter from falling in. Above this limit, black holes essentially blow themselves apart from internal pressure. Even at maximum efficiency, a small black hole would need almost the full age of the early universe to grow into a billion solar mass giant. Webb found these giants when the universe had not yet been alive long enough to allow it. This is not a small inconsistency. It is a brick wall. Astronomers have proposed several explanations. One idea is that the first black holes did not start from collapsed stars. Instead, they may have formed directly from huge collapsing gas clouds. These so-called direct collapse black holes could have started life with thousands or even millions of solar masses, giving them a head start. This idea is plausible, but has never been directly observed. Another theory suggests that early black holes broke the Eddington limit through unusual conditions. Perhaps the extreme density of the early universe allowed gas to be funneled in faster than radiation could push out. Some simulations support this, but the conditions required are extreme even for cosmic standards. A third, more radical possibility involves primordial black holes. These would be relics of the Big Bang itself, formed in the first fractions of a second. If they existed, they could have grown into supermassive monsters far more quickly. This idea remains speculative, but has gained more attention since Webb's findings. Whatever the answer is, one fact stands clear. The universe was producing supermassive black holes faster than current physics allows. This raises a deeper question. If black holes appeared so early, then galaxies must have been built with their massive companions almost from the beginning. That changes the entire model of how galaxies form. It means the giants did not grow with their galaxies. They may have grown first, shaping everything around them. This new picture of cosmic infancy contains another disturbing puzzle. Galaxies should not have looked organized so early. Yet many of them did, and the next discovery makes that even harder to explain. When astronomers look at the modern universe, they see two main types of galaxies: round, blobby ellipticals that look like cosmic clouds of stars, and flat, swirling disks that look like glowing pancakes. Spiral galaxies belong to the disk family. Disks are the homes of most stars in the cosmos, including our own Sun, which orbits inside the flat plane of the Milky Way. Disk galaxies require something special to form. They need a stable rotation. They need gas that can settle into a thin, organized layer. They need time to cool and smooth out. The traditional model placed the first true disks somewhere around 4 to 6 billion years after the Big Bang. Webb found them far earlier than that. In the deepest survey images, astronomers noticed something startling. Galaxies that existed only 1 to 2 billion years after the Big Bang already had clean, flat, rotating disks. Some had spiral arms. Some had central bulges. Many looked nearly identical to galaxies in the modern universe. The further Webb looked, the more disks appeared. A team at the University of Manchester ran the numbers. They expected disk galaxies to make up only a small percentage of early galaxies, maybe 10%, maybe less. Instead, more than half showed clear disk shapes. The early universe was not the messy, blobby place that simulations predicted. It was already organized. This is the disk galaxy problem. Disks are fragile. They can be destroyed by mergers. They can be disrupted by violent star formation. They can be torn apart by gravitational chaos. The early universe was supposed to be full of mergers, full of violence, full of chaos. So how did so many galaxies manage to settle into thin, clean, rotating disks so quickly? There are a few possible answers, each with its own problems. One theory says that cold gas was more abundant in the early universe than expected. This cold gas could fall into galaxies smoothly, rather than crashing in with high energy. Smooth infall means smoother disks. The trouble is that current models predict early gas should be hot and turbulent, not cold and orderly. Another theory suggests that mergers in the early universe were not as destructive as feared. If young galaxies collided gently or merged in ways that preserved rotation, then disks could survive. But that contradicts the assumption that the early universe was a violent place. A third theory claims that dark matter halos, the invisible scaffolding holding galaxies together, formed faster and more uniformly than expected. A more stable scaffolding would allow disks to assemble earlier, but this would require us to update the timing of dark matter structure formation. None of these ideas fully solves the puzzle. Simulations still struggle to reproduce the abundance of early disks Webb keeps finding. The problem is bigger than just shapes. Disk galaxies represent organized motion. They represent calm. They represent maturity. The early universe, by every theory, was supposed to be the opposite. It was supposed to be turbulent and immature. Webb is showing us that the cosmic toddler may have actually been a teenager in disguise. This raises a possibility that researchers have only recently started to take seriously. Maybe the early universe ran on different rules than we believe. Maybe its physics, at least temporarily, allowed structures to form with strange ease. Another deeply strange Webb discovery seems to support that possibility, and it involves tiny, glowing objects scattered across the early cosmos, hiding a secret no one expected. Among the most haunting discoveries Webb has made in the early universe is something simple in appearance, but staggering in implication. They are called little red dots, not stars, not normal galaxies, just small, intensely red glowing points scattered across the deep field surveys. When astronomers first noticed them, they assumed they were just background galaxies, faint and distant. But the more they studied these dots, the stranger they became. The colors did not match any familiar object. Their brightness was unusual. Their compactness was even more unusual. They were tiny, often appearing no bigger than a single point, yet they radiated with intense energy. Most importantly, they appeared in galaxies that existed when the universe was only about 500 million to 1 billion years old. Then came the analysis that shocked the field. Spectroscopic studies revealed that many of these little red dots seemed to host supermassive black holes, not small ones, massive ones, with masses far heavier than anything theory said could exist at that age. In some cases, the black hole appeared to weigh nearly as much as the entire host galaxy itself. This is where the real problem appears. In the modern universe, supermassive black holes are usually only a fraction of a percent of their galaxy's mass. The relationship is famously tight. Big galaxies have proportionally big black holes. Small galaxies have proportionally small ones. This balance is one of the most reliable patterns in modern astrophysics. Webb's little red dots break that pattern completely. They suggest that the early universe contained galaxies whose black holes were not just keeping up, but dominating. Some appear to be 100 times larger relative to their galaxy than they should be. This means the early universe might have grown black holes first, with galaxies forming around them later. That is the opposite of what most models assume. Usually, the galaxy comes first, and the central black hole grows along with it. The discovery has triggered a flood of new theories. One idea suggests that the first generation of stars were so massive they collapsed almost immediately into black holes, skipping the long evolutionary process that produces small black holes today. These primordial giants would then attract gas at incredible rates, growing into supermassive monsters far ahead of their galaxies. Another theory suggests that little red dots might be extreme examples of a phenomenon called direct collapse. Instead of forming through stellar death, gas clouds in the early universe could have collapsed straight into massive black holes. This would explain the speed of growth, but it requires conditions that have never been observed. A third theory takes a more unsettling angle. Some researchers believe these dots might be glimpses of physics we do not understand. Perhaps the universe's early matter behaved in ways that our equations cannot describe. Perhaps the early cosmos had a brief window where black holes formed at impossible rates. What makes the little red dots even more eerie is their quantity. Webb has found hundreds. The early universe is dotted with them. Whatever they are, they were common. These tiny crimson points may turn out to be the most important discovery of the Webb mission. They hint that the universe's earliest moments were stranger than anyone imagined. The next problem makes the picture even more confusing, because Webb did not just find too much in the early universe. It also failed to find something that should be there. In the standard model of the universe, dark matter is the invisible glue that builds everything. It does not emit light. It does not interact much with regular matter. It only pulls. According to simulations, dark matter clumps together first, forming a vast cosmic skeleton. Galaxies then grow inside these clumps. The simulations make a clear prediction. Around every large galaxy, there should be many small ones. Hundreds, in fact. These are called dwarf galaxies, and they are supposed to swarm around bigger galaxies like bees around a hive. The Milky Way should be surrounded by hundreds of them. So should Andromeda. So should every massive galaxy in the universe. The problem is, we cannot find them. Astronomers have searched for decades. They have used Hubble. They have used radio telescopes. They have used ground-based observatories. The number of dwarf galaxies they find is a tiny fraction of what the models predict. This puzzle is known as the missing satellites problem, and it has haunted cosmology for years. When James Webb launched, many hoped its incredible sensitivity would solve the issue. Webb can detect objects that are dimmer and farther than anything before. It should be able to see faint dwarf galaxies hiding around larger ones. Webb did indeed find new dwarf galaxies, but not nearly enough. In some cases, it actually made the problem worse. The early universe, where these dwarfs should be plentiful, looked surprisingly empty. This was not what astronomers expected. If dark matter behaves the way simulations claim, the early universe should be full of small clumps that eventually become dwarf galaxies. Webb's deep observations should have captured them in large numbers. Instead, the data showed a relatively smooth distribution of light, with fewer dwarfs than predicted. A few possibilities have been proposed. One is that dwarf galaxies exist but are too faint for even Webb to see. Some may have been disrupted or absorbed by larger galaxies. Some may have formed almost no stars at all, leaving them invisible. This idea assumes that the dark matter framework is correct, but that visible matter behaves in ways we have not fully measured. Another possibility is more radical. It suggests that dark matter itself behaves differently than the standard cold dark matter model assumes. Some scientists believe dark matter could be slightly warm. Warm dark matter would smooth out small clumps in the early universe, producing fewer dwarfs from the start. This idea remains controversial, but is gaining traction. A third, more disturbing possibility suggests that the cosmic skeleton built by dark matter may have been misjudged altogether. If dark matter's behavior is different than expected, then the entire architecture of the universe, including how galaxies cluster, may need revision. Webb is now testing these ideas with unprecedented detail. Each new survey adjusts the numbers, but the missing dwarf problem refuses to disappear. The early universe simply does not look as crowded as the simulations demand. This is one of those moments where absence speaks louder than presence. Something fundamental seems to be off about how matter formed at the smallest scales. And the next discovery makes the situation even stranger. Webb found something else in the early universe that should not be possible. Tiny galaxies that should be dim, but instead shine with the brilliance of massive cosmic giants. When Webb began studying the dimmest, most ancient galaxies in the cosmos, scientists expected to see soft, faint glows. The earliest galaxies should be small, weak, and humble. They should look like distant candles, not lighthouses. That is what every model predicted. Instead, Webb saw torches. Some of the smallest galaxies in the early universe were shining with intensities that stunned the research teams. A few of these tiny ancient galaxies, no larger than 10% of the Milky Way's size, were pumping out as much light as galaxy clusters in the modern universe. Their luminosity was off the chart. The math behind their brightness was even more confusing. Brightness in galaxies usually comes from stars. The more stars, the brighter the galaxy. But stars need time, gas, and stable conditions to form. In the early universe, conditions were rough, gas was hot, time was short. Star formation should have been slow, yet these tiny galaxies were producing stars at breakneck speed, sometimes hundreds of times faster than typical galaxies today. Imagine a small village producing more electricity than an entire country. This kind of star formation is called extreme starbursting. It happens occasionally in modern galaxies during mergers or violent events, but seeing it in the early universe, in such tiny galaxies, in such large numbers, is completely unexpected. A team at the University of Edinburgh examined dozens of these objects. They found that the brightness levels could not be explained by normal star formation alone. Something was supercharging these galaxies. Either they were converting gas into stars with near-perfect efficiency, or they were lit up by something more exotic than starlight. That second possibility is where the science becomes uncomfortable. Some researchers believe these galaxies might host massive black holes feeding on infalling matter, producing enormous amounts of light. This could explain the brightness, but it would mean that massive black holes existed in tiny galaxies far earlier than thought. That contradicts the assumption that black holes grow with their galaxies. Others suggest that the early universe may have had a different kind of star altogether. Population 3 stars, the very first stars to form, are predicted to have been hundreds of times more massive than today's stars. They would burn at extreme temperatures, releasing massive amounts of energy. If many population 3 stars were active in these tiny galaxies, the brightness could be explained, but their existence has never been definitively confirmed. A third explanation, offered cautiously by a few teams, suggests that the universe's early star formation simply behaved differently than the modern era. The chemistry was simpler, the gas was denser in some regions, and gravitational conditions may have allowed faster collapse. If this is true, our entire understanding of the first generations of stars must be revised. What is most striking is the consistency of the brightness. Tiny galaxies all across the early cosmos seem to glow with strange, intense light. This is not a one-off anomaly, it is a pattern. Webb is showing us that the early universe was a noisy, fiery place. Small galaxies behaved like cosmic furnaces. They formed quickly, burned brightly, and grew faster than physics expected. This challenges the assumption that the cosmos started slowly and cautiously. It also raises the next mystery. If these galaxies produced so many stars so quickly, they should have already created heavy elements, things like iron, oxygen, and carbon. And yet, when Webb looked deeper, the chemistry told a story that should not be possible. Every atom heavier than helium was forged inside stars. That is one of the oldest rules in astronomy. Hydrogen and helium were born during the Big Bang itself. Everything else, the iron in your blood, the oxygen in the air, the carbon in your bones, the silicon in your phone, all of it was cooked inside stars and scattered across space when those stars exploded. This process takes time, a lot of time. A first generation of stars must form. They must burn through their lives. They must explode as supernovae, blasting their elements outward. Then a second generation of stars must form from the enriched gas. Only then does the universe begin to contain meaningful amounts of heavy elements. According to standard models, this enrichment process should take at least 1 to 2 billion years. Webb found heavy elements in galaxies that existed less than 500 million years after the Big Bang. This is the chemistry problem, and it is one of the most uncomfortable surprises Webb has produced. Spectroscopic analysis of distant galaxies revealed traces of iron, oxygen, carbon, and silicon. In some cases, the levels were close to those of modern galaxies. That means the early universe somehow managed to forge, distribute, and recycle heavy elements at a speed that should not be possible. A team in Germany rechecked the measurements multiple times. They suspected contamination, errors, or misidentifications. The data held, the early galaxies truly contained heavy elements far ahead of schedule. There are several possible explanations, but each one stretches current physics. One idea is that the first stars, the population 3 giants, were enormous and short-lived. They could have exploded almost immediately, scattering heavy elements before normal star formation could even begin. This is plausible, but it would require these monster stars to be far more numerous and active than current models suggest. Another idea is that early supernovae blew through galaxies with extraordinary force, mixing heavy elements into vast volumes of gas in record time. The early universe was smaller, denser, and more compact, so chemical mixing could have been faster than today. But even this idea struggles to explain the high enrichment Webb is seeing. A third theory suggests that the timeline of cosmic history must be expanded. If the universe started slightly earlier than 13.8 billion years ago, then the chemistry problem becomes easier to solve. But this would force a major revision of cosmic dating. A fourth theory, more controversial, proposes that some unknown process produced heavy elements outside of stars. This would be a radical departure from established science, and most astronomers consider it unlikely. But the chemistry problem is so severe that even fringe ideas are being taken seriously. The deeper concern is that the early universe seems to have been chemically advanced from the start. Galaxies were not just forming, they were recycling. They were enriching themselves. They were preparing the ingredients for future life with surprising speed. This suggests that the cosmic timeline may be more compressed than we thought. The universe did not crawl through its early years. It sprinted. The next discovery digs even deeper into this question. Because Webb did not just find heavy elements where it shouldn't, it also failed to find something that should be there. Something so important that its absence reshapes our understanding of the very first stars. In the entire story of the universe, no stars are more important than the very first generation. They are called population 3 stars. They formed from the pure hydrogen and helium left over from the Big Bang, with no heavier elements to slow them down. Without these elements, the gas could not cool easily, which means population 3 stars had to be enormous to ignite. Theories suggest that they were giants, possibly hundreds of times the mass of the Sunday. They burned hot, blue, and bright. They lived only a few million years before exploding as massive supernovae, scattering the universe with the first traces of heavy elements. These stars are essential to the cosmic story. Without them, no galaxies, no planets, no life, no us. Yet, despite their importance, no one had ever directly observed a population 3 star. Astronomers hoped Webb would change that. Its infrared sensitivity makes it the perfect instrument for detecting the dim, ancient light from the universe's first stars. Many believed the discovery was inevitable. Years into the mission, Webb still has not found them. This is one of the most quietly disturbing absences in modern astronomy. If population 3 stars existed in the way models predict, Webb should be detecting them in small bursts in the earliest galaxies. They should leave clear chemical signatures in the surrounding gas. They should illuminate the ionized regions around them with very specific patterns. Webb has searched for these signatures. The signals are not appearing. or when they do appear, they are far weaker and more rare than expected. This raises a serious question. Did population 3 stars exist at all? Or did they exist, but in different forms than predicted? Some teams believe that population 3 stars might have been smaller than theory suggests. If their masses were lower, they would burn cooler and longer, leaving fewer traces. They could blend in with later generations of stars and become difficult to identify. Webb may simply be missing them due to confusion with other objects. Others propose that population 3 stars existed only briefly and in tiny pockets of the early universe. Their lifetimes might have been so short and their numbers so small that detecting them is nearly impossible. A third group raises a more uncomfortable possibility. Maybe population 3 stars formed in unusual ways that we do not understand. Maybe the universe's first stars did not behave like the giant fireballs we expect. Maybe the chemistry of the early gas was different. Maybe there was a hidden process that suppressed their formation altogether. The absence has consequences. If population 3 stars are missing, then early heavy element production must have come from somewhere else. This loops back into the chemistry problem from earlier. Something forged the early elements at incredible speed, but the suspected source is not showing up. This is a deep mystery. Population 3 stars are foundational to our cosmic story. Their existence is built into nearly every model of how galaxies, planets, and life formed. If Webb continues to fail to detect them, the story of the first generation of stars may need to be rewritten entirely. The deeper Webb looks, the more the early universe seems to behave in ways that defy expectations. And the next discovery makes that even more clear, because Webb found something unexpected, coating young galaxies, something that should not be possible at all. When astronomers think of dust in space, they do not imagine the kind that gathers on shelves. Cosmic dust is far more important. It is made of microscopic grains of silicates, carbon, and metals. It absorbs starlight, glows in infrared, and shapes how galaxies grow. Most importantly, dust is the building block of planets. Without it, rocky worlds and life as we know it cannot exist. Dust is also a problem for the early universe. Cosmic dust requires multiple generations of stars to produce. Stars must form, age, and explode. Their leftovers must mix with cool gas. Only then can dust grains slowly build up. This process takes hundreds of millions of years. Some models suggest it takes more than 1 billion. According to standard physics, the earliest galaxies should be almost completely dust-free. Webb saw the opposite. Galaxies that existed only a few 100 million years after the Big Bang already contained significant amounts of dust. Some of them had so much dust that their light came out muffled and reddened, similar to dusty galaxies in the modern universe. The dust was not faint, it was abundant. This was not what astronomers expected. They had hoped to see clean, pristine, early galaxies, full of bright young stars and almost no dust. Instead, they found galaxies that looked surprisingly mature, even chemically advanced. A research team in the Netherlands led one of the major analyses. They tested every possible explanation. Could the dust be coming from some background source? No. Could it be a misinterpretation? No. Was the redness from extreme star formation? Partially, but not enough to account for all of it. The dust was real, and it was abundantly present. Several theories try to explain this surprising abundance. One suggests that the first stars exploded in massive supernovae, dispersing dust quickly. Population 3 stars, if they existed, would have produced dust grains during their final explosions. Some early galaxies could have been seeded with dust from this first wave of cosmic violence. Another theory proposes that early dust grains formed in unusual ways. Cold gas in dense clumps might have allowed dust to grow much faster than typical conditions allow. This is plausible, but the physics is not fully understood. A third theory, more puzzling, suggests that early galaxies recycled material at extraordinary speeds. Generation after generation of stars formed, exploded, and scattered material in compressed timeframes. The chemistry in these galaxies advanced so quickly that they produced dust as if billions of years had passed in only a few 100 million. Whatever the answer, the dust problem confirms a pattern Webb keeps revealing. The early universe was not slow, it was not gentle, it was not minimalist. It was already deeply enriched, organized, and active in ways the standard model did not predict. Dust is also a clue about life. If dust formed early, then planets could have formed early. And if planets formed early, then conditions for chemistry and possibly life could have appeared sooner than anyone imagined. This brings us to the next discovery, which carries some of the most stunning implications of all. Webb did not just find dust around early galaxies. It also found a strange chemical signal on a distant world that may shake the boundaries of biology. When the James Webb Space Telescope began studying exoplanets, the results came quickly, but few discoveries hit harder than the analysis of a world named K2-18b. This planet sits about 120 light-years from Earth, orbiting a small red dwarf star. It is roughly 2.5 times the size of Earth and nearly 9 times its mass. K2-18b is part of a category of worlds called sub-Neptunes. These are planets larger than Earth but smaller than Neptune, and they are common throughout the galaxy. Until Webb, they remained mostly mysterious. When Webb examined the atmosphere of K2-18b, the results startled the scientific community. The data showed clear signs of methane and carbon dioxide. That alone was groundbreaking, since detecting these gases on a distant world is extremely difficult. But what came next was the bombshell. The atmosphere also contained a tentative hint of dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by living organisms. Tiny ocean microbes called phytoplankton release it in massive amounts. There is no known geological process that produces dimethyl sulfide in significant quantities. If the signal is real, it is one of the most striking biosignatures ever detected. Astronomers were careful with their words. The team made it clear that the detection was not confirmed. The signal was weak. More observations were needed. The team also stated that an alternative explanation could be a unique chemistry happening on this strange world. K2-18b is suspected to be a Hycean world, meaning a planet with a hydrogen-rich atmosphere covering a global ocean of liquid water. If true, its chemistry would behave very differently from Earth's. Methane and dimethyl sulfide could possibly form through processes we do not yet understand. Still, the implications are enormous. For the first time in human history, a real chemical hint that might suggest life was found on a planet outside our solar system. Even if the dimethyl sulfide turns out not to come from biology, the discovery shows that Webb is capable of sniffing the atmospheres of distant worlds in extraordinary detail. The age of remote biosignature hunting has officially begun. Several major observation campaigns are now planned. Webb will repeatedly study K2-18b. Future telescopes will follow up with even more sensitive measurements. The world is waiting to see whether the dimethyl sulfide signal grows stronger or fades into noise. But the bigger question is not just about one planet. If life-related signals can appear on a sub-Neptune, how many similar worlds might harbor strange or even living chemistry? The galaxy has billions of these planets. Webb has only scratched the surface. In the coming years, it will examine dozens more atmospheres. Some may show unusual gases. Some may reveal even stranger chemistry. Some may produce signals far harder to explain than methane. This is the start of a new era in astronomy. The discovery of biosignatures, real or potential, has shifted from theoretical conversation to active scientific data. K2-18b is now one of the most studied planets in the night sky, and its mystery may take years to unravel. Webb's reach extends even further. It can examine objects so distant that they break the records of every previous telescope. And one of those records is a single, lonely star burning at the edge of the observable universe. In a sky full of galaxies, clusters, and stellar nurseries, Sometimes a single star tells the most powerful story. That is exactly what happened when Webb turned its mirror toward an object discovered first by the Hubble Space Telescope. A star so distant that it set a new record for the most far-flung individual star ever observed. Its name is Arundel. The light from Arundel began its journey when the universe was less than 1 billion years old. By the time it reached Webb's mirror, it had traveled for more than 12.9 billion years. Arundel is so far away that under normal circumstances, no telescope on Earth or in space could possibly resolve it as a single point. The reason we can see it at all is something almost magical. A massive galaxy cluster sits between Earth and Arundel. Its enormous gravity acts like a giant lens, bending and magnifying the light passing through it. This effect, known as gravitational lensing, stretched and amplified Arundel's light into a thin streak. The lensing made the star visible against all odds. Hubble first spotted Arundel as a faint dot. Webb confirmed its identity with sharper detail. The new measurements suggested Arundel might be a binary star system with two giant blue stars orbiting one another. Together, they could weigh many dozens of solar masses, possibly hundreds. This discovery is more than a record, it is a window. Stars from this era are extremely difficult to study. They formed when the universe was young and hot. Their chemistry should be primitive, with very few heavy elements. Studying Arundel gives astronomers a chance to peek into a stellar population that has long been buried under cosmic distance. The chemistry of Arundel may even help solve a different mystery. If the star's spectrum shows surprisingly low metal content, it could support theories about early star formation. If it shows higher metals than expected, it could deepen the mystery of how heavy elements appeared so quickly in the early universe. A team at the University of Cambridge has been studying Arundel's light carefully. Each new observation refines what we know. Some early indications suggest that the star has properties unlike anything in the modern Milky Way. Its light hints at extreme temperatures, intense radiation, and a structure that seems alien compared to today's stars. This raises a deeper question. Arundel may be only a few 100 million years younger than the universe itself. In its lifetime, it could be witnessing a chapter of cosmic history we can barely imagine. Whatever happens to this giant blue star, its existence forces astronomers to reconsider what was possible in the first billion years of the universe. Arundel may not stay the most distant star for long. Webb is expected to find more lensed objects in the coming years, with the chance of revealing even older single stars. But Arundel is the first, the pioneer, the brilliant outlier that taught us that even individual stars from the cosmic dawn can speak. This discovery also marks something important. It shows that Webb is capable of resolving objects far smaller and far more distant than anyone believed possible. It is not just looking at galaxies, it is touching individual stars across the abyss of cosmic time. And the next mystery comes from a different angle altogether. Webb is now exposing strange behavior in galaxy rotation, behavior that may finally reveal the truth about dark matter. For nearly a century, astronomers have known something is wrong with how galaxies spin. When stars orbit the center of a galaxy, they should follow predictable rules. Stars closer to the center should move faster. Stars farther from the center should move slower. This pattern is similar to how planets orbit the Sun, where Mercury races and Neptune crawls. Galaxies do not follow this rule. In every galaxy ever measured, stars in the outer regions move just as fast as stars in the inner regions, sometimes faster. There is no good explanation for this, using only visible matter. The galaxies should be tearing themselves apart. They are not. This problem led to the introduction of dark matter, invisible mass that surrounds galaxies in massive halos, providing extra gravity to hold everything together. Dark matter became one of the foundational pillars of modern cosmology. We have never directly detected it, but its effects have been observed everywhere. Webb has now opened a new chapter in this mystery. By studying distant, ancient galaxies, Webb is providing astronomers with the clearest measurements ever made of how galaxies rotated when the universe was young. The results are not what scientists expected. Some ancient galaxies appear to rotate more like miniature versions of modern spiral galaxies, suggesting that dark matter halos were already in place soon after the Big Bang. This is surprising, since simulations predicted that early galaxies should have less developed dark matter scaffolding. Other ancient galaxies behave even more strangely. Their rotation curves do not match what dark matter alone should produce. Some galaxies rotate too fast. Others rotate too slowly. The diversity of motion in the early universe is far greater than expected. A research team in Italy analyzed the rotation patterns of dozens of early galaxies. They found that the variation was so extreme that no single model could explain everything. Some galaxies looked perfectly normal. Others had rotational behavior that hinted at unusual gravity, unusual gas distributions, or unusual dark matter concentrations. This raises a serious possibility. Dark matter, if it exists, may not behave the same way in the early universe as it does today. Some scientists propose that dark matter could have been more dynamic in the cosmic dawn, settling into halos slowly and unevenly. Others suggest that early galaxies might have undergone violent gravitational events that disrupted their rotation patterns. Still, others wonder whether the whole concept of dark matter needs to be revised. A growing number of researchers have started exploring alternatives. Modified gravity theories, where the laws of motion change at very low accelerations, are gaining renewed interest. These theories were once considered fringe, but are now being seriously studied because of mounting anomalies. Webb cannot definitively prove or disprove dark matter, but it is forcing astronomers to face uncomfortable possibilities. Either dark matter is more complex than the standard model suggests, or our understanding of gravity itself may be incomplete. The early universe is the perfect testing ground. The conditions were extreme, the matter was dense. The gravitational behavior is recorded in the rotation patterns of distant galaxies. As Webb continues to gather data, the picture will become clearer. But for now, the rotation puzzle is one of the most important open questions in modern science. The next discovery pushes Webb's record even further. The telescope has now found a galaxy whose distance breaks every previous limit, and its existence may reshape our entire understanding of cosmic history. In May of 2024, a discovery hit the astronomy world like a thunderclap. Webb confirmed the existence of a galaxy so far away that its light had been traveling for nearly 13.5 billion years. Its name is JADES GS 14-0, and at the time of discovery, it became the most distant galaxy ever observed. The numbers behind it are difficult to grasp. We are seeing this galaxy as it appeared only about 290 million years after the Big Bang. That is the cosmic equivalent of seeing a baby take its first breath. In the universe's overall lifetime, this galaxy is a newborn, captured in mid-formation. Yet what Webb saw made no sense. JADES GS 14-0 is not small, it is not faint, it is not primitive. It is a fully developed galaxy with a measurable size, structure, and brightness that competes with galaxies much later in cosmic history. The galaxy appears to span more than 1,600 light-years in diameter and contains hundreds of millions of solar masses worth of stars. This shocked the research community. Galaxies of this size and brightness should not be possible at this point in cosmic history. According to standard models, only tiny clumps of forming material should exist that early. But JADES GS said 14-0 looks like it skipped multiple steps in galactic evolution. Even more striking was the chemistry. The galaxy showed signs of oxygen, suggesting that several generations of stars had already formed, exploded, and seeded their environment with heavy elements. This further compresses the timeline. To have oxygen this early, the universe would have needed to crank out massive stars and supernovae at extraordinary speed. A research team, led by scientists from the United States and Europe, compared the galaxy to dozens of other early objects. The comparison only deepened the mystery. JD's GSZ 14-0 is not alone in being too advanced. It belongs to a growing family of galaxies that defy expectations. Some scientists propose that early galaxies could have undergone explosive bursts of star formation, allowing them to grow enormous in short bursts. This would solve some of the size and brightness questions, but it would still require unusually efficient star production. Others suggested that early dark matter halos may have been larger or denser than previously thought. A bigger gravitational scaffold would allow more gas to gather quickly, producing massive galaxies faster than expected. But this idea forces a rewrite of dark matter behavior in the cosmic dawn. A more radical theory proposes that the early universe may have had brief eras of extreme activity. Perhaps physical conditions were temporarily different, allowing structures to form at speeds we cannot reproduce in current models. This is speculative, but is gaining attention as more data flows in. JD's GSZ 14-0 is also a cultural milestone. It marks the moment astronomy took a step into a regime where the standard model of cosmology no longer comfortably fits. Each new record-breaking galaxy adds more pressure to existing theories. Many researchers believe that the timeline of the universe will need to be revised in the coming decade. This galaxy is not just a distant point of light. It is a warning. It is telling us that the cosmic dawn was busier, brighter, and more advanced than anyone thought. And just when scientists believed nothing else could surprise them, Webb opened a new window into the cosmic dawn itself, revealing a universe far stranger than predicted. The cosmic dawn refers to the period when the first stars and galaxies switched on, lighting up the universe after a long, dark age. For more than 300 million years after the Big Bang, the cosmos was filled with neutral hydrogen gas. No stars existed, no galaxies, just a thick, dark fog stretching across all of space. Then something changed. The first stars ignited. Their radiation began to ionize the hydrogen around them, slowly burning away the cosmic fog. This process is called reionization. It is one of the most important events in the universe's history, and astronomers have spent decades building models to predict what it should look like. Webb has now observed the cosmic dawn directly, and what it found does not match the predictions. According to the standard timeline, reionization should have started gently. Faint clusters of hydrogen should have begun glowing softly. The earliest galaxies should have been small, dim, and rare. The transition from dark to light should have been a slow, gradual process. Webb is showing us a different story. The cosmic dawn appears to have been violent, fast, and chaotic. Galaxies are brighter than expected. Star formation is faster than expected. Reionization seems to have begun earlier and proceeded more aggressively than models predicted. The light from this era, captured by Webb, shows patterns that suggest the universe was far more active during its first half-billion years than anyone believed. A team in Japan reviewed the early Webb observations and concluded that the cosmic dawn was a far more dramatic event than the textbooks describe. They found that the light from this era was concentrated in pockets of intense star formation, with vast empty regions in between. The universe was not lighting up slowly, it was lighting up in furious, scattered bursts. This kind of patchy, aggressive reionization is hard to explain. The standard model predicts a smoother process, but the data shows clear evidence of irregular activity. Some regions appeared to ionize quickly, others remained dark for much longer. The universe seems to have followed a pattern that no current simulation can fully recreate. This raises difficult questions. Why was star formation so concentrated? What kind of galaxies powered such intense reionization? Why is the cosmic timeline showing signs of compression? One theory suggests that the first galaxies were equipped with massive black holes that emitted ionizing radiation alongside starlight. This would explain the speed and intensity of reionization, but raises further questions about how those black holes formed so early. Another theory proposes that early stars may have been hotter and more luminous than predicted. If so, they would have produced enormous amounts of ultraviolet light, accelerating the ionization process. But this requires conditions that current chemistry models have difficulty supporting. A third theory takes the boldest position. It suggests that the early universe may have followed slightly different physical rules during its first 100 million years. Perhaps gravity behaved differently. Perhaps gas behaved differently. Perhaps the universe operated on a faster, more violent rhythm before settling into the calm cosmic expansion we measure today. The cosmic dawn was supposed to be a quiet age that gradually awakened. Webb shows us that it may have been a thunderous awakening, full of explosive light and aggressive structure. The universe roared into being. It did not whisper, and the more Webb looks, the stranger the picture becomes. Some galaxies are now appearing to spin in a direction that should not be possible. Galaxies rotate. That is one of the most basic, observable facts in the universe. Stars, gas, dust, and dark matter all swirl around a galactic center, following predictable patterns shaped by gravity and the early conditions of cosmic formation. For decades, astronomers assumed that the rotation directions of galaxies should be roughly random. Some galaxies spin clockwise as we view them, others spin counterclockwise. According to the standard model of cosmology, this distribution should be balanced. The universe is supposed to be uniform. There should be no preferred direction. Webb is showing us that this assumption may be wrong. When the telescope studied vast samples of galaxies across enormous distances, researchers noticed something unexpected. The number of galaxies spinning in one direction did not match the number spinning in the other. The discrepancy was small, but persistent. Galaxies seem to slightly prefer one rotational orientation over the other. This may not sound dramatic, but the implications are serious. The standard cosmological model assumes that the universe is isotropic. That means it should look the same in every direction. There should be no cosmic preference, no overarching tilt, no hidden alignment. If galaxies are rotating in a non-random way, then something is breaking that symmetry, and nothing in the standard model predicts a force that would cause this. A team at Kansas State University has been studying this phenomenon for years. Using both Hubble and Webb data, they confirmed that the asymmetry exists across multiple regions of the sky. The patterns persist even when sampling techniques are adjusted. Even when statistical biases are removed, something is causing galaxies to favor a slight rotational bias. There are several theories trying to explain this strange behavior. One theory suggests that the universe itself might have a tiny, nearly imperceptible rotation. If the entire cosmos is spinning slowly on a massive scale, then galaxies could inherit a preferred rotation direction. This idea has been around for decades, but has never been taken seriously until recent observations began revealing patterns that hint at it. Another theory proposes that early dark matter dynamics could have introduced a slight directional bias in galaxy formation. If dark matter behaved unevenly during the early universe, galaxies could have inherited subtle differences in spin distribution. A third theory connects the rotation puzzle to the broader idea of cosmic anisotropy. Some scientists have noticed that the cosmic microwave background also contains tiny features suggesting subtle preferred directions in space. If the early universe had directional asymmetries, then galaxies forming inside those structures could carry their imprint. The most provocative theory is the simplest. Maybe the universe is not as uniform as we believed. Maybe its earliest moments produced a small but real cosmic tilt that influences everything we see. If that is true, the foundations of cosmology will need a serious revision. Webb cannot prove this directly, but its observations are giving researchers data clean enough to test these ideas. The rotation puzzle is no longer fringe. It is moving into mainstream discussions, challenging the assumption that the universe has no preferred direction. This raises a deeper concern. If our universe is hiding subtle asymmetries, what else might be hiding? The next discovery answers part of that question by revealing a galaxy whose central black hole is so enormous that it is reshaping our understanding of cosmic balance. Galaxies and their central black holes usually grow in sync. The bigger the galaxy, the bigger the black hole. This relationship is so consistent that astronomers refer to it as a cosmic law of proportions. In the modern universe, a typical supermassive black hole weighs about 0.1% of its host galaxy's stellar mass. Webb just shattered that rule. In the early universe, the telescope discovered galaxies hosting black holes with masses far greater than their proportions should allow. In one case, the black hole appeared to be larger than the entire stellar content of the surrounding galaxy. That should be impossible. It would mean the black hole grew first, and the galaxy formed around it later, almost like a city built around a single massive monument. This was supposed to be the opposite of how galaxies evolve. The discovery emerged from a careful analysis of the so-called little red dots and other ancient bright sources Webb has been mapping. As researchers measured the mass of the central black holes, the numbers came back staggering. Many were thousands of times more massive relative to their host galaxies than expected. Some galaxies looked like they were dominated almost entirely by their central monsters. This forced astronomers to ask a difficult question. Did black holes lead the construction of early galaxies? Did they form first, then drag in surrounding gas to build their galactic homes? If so, the entire model of galactic evolution may need to be rewritten. A team at MIT analyzed dozens of these early black hole-dominated galaxies. They concluded that the early universe seemed to have produced massive black holes far more efficiently than later eras. These were not simply oversized, they were record-breaking, with weights that defied typical formation theories. Scientists have proposed several explanations. One is direct collapse. In this scenario, certain regions of the early universe contained enormous gas clouds that did not fragment into stars. Instead, they collapsed straight into black holes weighing thousands or millions of solar masses. Once formed, they could grow rapidly through accretion, becoming massive long before their galaxies caught up. Another idea is that the first generation of stars produced unusually large stellar black hole seeds. If the first stars were truly enormous, their leftover black holes would have been correspondingly massive. With time and unrestricted accretion, they could grow into the giants Webb is finding. A third, more controversial theory suggests primordial black holes formed during the Big Bang. These hypothetical objects could have ranged in size from tiny to galactic, and if they existed, they could explain the abundance of massive black holes Webb is detecting. Whatever the mechanism, the data is pointing to a strange and humbling truth. The early universe seems to have built black holes faster than galaxies. The cosmic balance we see today may have started from a chaotic, lopsided era where black holes ruled the cosmos. This rewrites the cosmic story in a way that is difficult to overstate. It means galaxies did not always lead the way. Black holes may have shaped the universe before galaxies even fully formed. Their gravity, radiation, and energy could have influenced star formation, gas distribution, and galactic structure from the very beginning. The deeper Webb looks, the more it shows that the early universe was dominated by extremes. And the next discovery comes from a completely different cosmic giant. Quasars, from the universe's infancy that should not be possible according to current black hole growth physics. Quasars are some of the brightest objects in the universe. They are powered by supermassive black holes feeding on enormous amounts of gas. As matter falls into the black hole, friction and gravity heat it to extreme temperatures, releasing more energy than entire galaxies. Some quasars shine with the brightness of trillions of suns combined. For years, astronomers have known that quasars existed in the early universe. Hubble found a few. Ground-based telescopes found a handful more. But Webb has dug into the cosmic infancy with unprecedented detail, and what it discovered has reignited one of the biggest puzzles in modern astrophysics: the seed problem. The seed problem asks a simple question: how did the very first quasars form so quickly? A quasar requires a supermassive black hole at its core. To produce such a powerful object, a black hole must grow into millions or billions of solar masses. Even at the maximum theoretical growth rate, This should take more than 1 billion years. That assumes a black hole starts with a healthy seed mass and feeds continuously with no interruption. Webb has now confirmed quasars existing only 700 to 900 million years after the Big Bang. Some appear even earlier. They are full-blown quasars, fed by gigantic black holes, glowing fiercely across cosmic distances. This should not be possible. To form so quickly, the original black hole seeds must have been already large from the start. Stellar mass black holes, the kind formed from collapsing stars, are not big enough to grow into supermassive monsters in such a short window. Even multiple mergers between stellar black holes cannot reach the required size in that timeline. Some researchers propose that early quasars must have been seeded by direct collapse black holes, formed from massive gas clouds during the cosmic dawn. These hypothetical seeds would weigh thousands or even millions of solar masses, allowing them to grow into supermassive giants in less time. The trouble is that direct collapse remains unproven. No one has ever directly observed it happening. Other theories propose primordial black holes, formed in the chaotic moments after the Big Bang. These would be ancient relics of the universe's first fractions of a second. If they existed, they could provide ready-made seeds capable of becoming quasars rapidly. This idea has gained renewed attention with each Webb finding, but it remains speculative. A more conservative theory suggests that early black holes broke the Eddington limit, the natural cap on how fast a black hole can grow. If the early universe contained dense, fast-cooling gas, infall could have proceeded at extreme rates. Some researchers refer to this as super-Eddington accretion. While theoretically possible, it requires unusual conditions to maintain over long periods. Whatever the mechanism, Webb is forcing astronomers to admit that the early universe was capable of producing supermassive black holes far faster than physics has comfortably allowed. The entire growth story of these monstrous objects may need to be revised. Quasars also act as cosmic spotlights. They illuminate the gas around them, revealing the chemical state of the early universe. Webb has been analyzing this light to learn more about the cosmic dawn. What it has found further deepens the seed problem. The gas around early quasars often shows surprising amounts of heavy elements, suggesting that intense star formation was already underway long before quasars should have lit up. The early universe is showing us a story far more dynamic than anyone predicted, and the next discovery exposes another layer of cosmic strangeness. Webb is detecting hints in early galaxy clustering that reveal a possible new behavior of dark matter. When astronomers map the universe, they do not just look at individual galaxies. They study how galaxies cluster together. Galaxies tend to gather along enormous invisible structures known as the cosmic web. This web is built by dark matter, which gravitationally pulls gas and galaxies into long filaments and dense knots. For decades, simulations have predicted exactly how galaxies should cluster in the early universe. The pattern depends entirely on the behavior of dark matter. If dark matter is cold and slow-moving, galaxies should cluster in a specific way. If it is warm or behaves differently, the pattern shifts. Webb is now exposing a clustering pattern that does not perfectly match the predictions. When the telescope mapped the locations of ancient galaxies, researchers expected to find them spread out in familiar patterns inherited from cold dark matter simulations. Instead, several teams reported unusual clustering features. Some early galaxies seemed too tightly grouped, others appeared too spread out. The cosmic web of the early universe looked subtly off. This raised an immediate question. Is dark matter behaving differently than the standard cold dark matter model predicts? A team in California compared Webb's clustering data to multiple dark matter models: cold dark matter, warm dark matter, fuzzy dark matter, and self-interacting dark matter. Each model predicts a slightly different pattern of how galaxies should gather in the cosmic dawn. The Webb data did not match the cold model perfectly. It showed enough deviation to suggest that other dark matter models may need serious consideration. This is a major shift in the field. Cold dark matter has been the dominant theory for decades. It assumes dark matter particles move slowly, allowing them to clump easily and produce small structures throughout the universe. This is the basis for almost every modern cosmological simulation. Warm dark matter, on the other hand, suggests slightly faster moving particles. This would smooth out small-scale structures, reducing the number of dwarf galaxies and altering early clustering patterns. Some Webb data hints that this model may fit observations more naturally. Fuzzy dark matter is a more exotic theory. It proposes that dark matter particles are extremely light and behave more like waves than particles. This would create soft, smooth distributions in the early universe. Some Webb observations have shown patterns that fit this idea, though the evidence is still preliminary. Self-interacting dark matter is another emerging theory. It assumes that dark matter particles can collide with each other under certain conditions. This would alter the formation of galactic halos and reshape early clustering. Webb's measurements have provided new tests for this model, though more data is needed. The bigger picture is unsettling. The dominant model of dark matter, the very foundation of modern cosmology, may not match what Webb is seeing in the early universe. This does not necessarily mean dark matter is wrong, but it strongly suggests that our understanding of its behavior is incomplete. Astronomers are now collecting larger samples to test the patterns more carefully. Each new survey adjusts the picture slightly, but the underlying trend remains. The cosmic web of the early universe was assembled in ways that current cold dark matter physics cannot fully explain. Webb is also peering far beyond galaxies. Its instruments can analyze the atmospheres of distant worlds with incredible precision, and the next discovery comes from one of the most studied exoplanets in modern astronomy, a planet whose atmosphere is shocking scientists in ways no one expected. WASP 39b is a giant planet about 700 light-years away. It is roughly the size of Saturn, but orbits its star so closely that its temperature soars beyond 1500 degrees Fahrenheit. Its year lasts only about 4 Earth days. It has been observed many times with telescopes around the world, but Webb saw it in a way no instrument had managed before. When Webb examined this scorching world, it produced the most detailed atmospheric chemistry analysis ever made on a planet outside our solar system. The results stunned the scientific community. For the first time, astronomers detected sulfur dioxide in an exoplanet atmosphere. This molecule is rare and very difficult to find on distant worlds. On Earth, sulfur dioxide is associated with volcanic activity and certain forms of industrial pollution. On WASP 39b, the sulfur dioxide was forming through a process called photochemistry, where intense ultraviolet radiation from the host star breaks apart molecules and triggers new chemical reactions. This was the first time photochemistry had ever been confirmed on another planet. The discovery means that exoplanet atmospheres are not just static layers of gas. They are dynamic, reactive environments where starlight produces chemistry similar to what happens in Earth's stratosphere. This is critical for understanding which planets could support life, since photochemistry plays an important role in shaping habitable conditions. Webb did not stop with sulfur dioxide. The telescope detected water vapor, carbon dioxide, carbon monoxide, sodium, and potassium. It mapped how these gases were distributed throughout the atmosphere. It studied how they reacted to changes in temperature and altitude. It revealed cloud structures, wind patterns, and even hints of haze layers high above the planet's surface. This level of detail had never been achieved for any exoplanet. For decades, researchers wondered whether telescopes would ever be able to study alien atmospheres so precisely. The Hubble Space Telescope had made some progress, but its sensitivity was limited. Webb pushed the boundaries far past what was thought possible. WASP 39b became a test case for the new era of exoplanet science. A team analyzing the data noted that the chemistry of this planet challenges traditional models. Some elements appeared at unexpected levels, Some chemical reactions were happening faster than expected. Some absorption features had patterns that hinted at processes still being studied. Each Webb observation produced new questions. The implications go far beyond WASP-39b. The methods used here can be applied to other planets, including potentially habitable ones. Scientists are now using the same techniques to study smaller, cooler worlds that may support liquid water. The hope is that one day, Webb will detect chemistry on a small rocky planet that mirrors signs of life. This kind of analysis is changing the entire field. Exoplanet research used to focus on simply finding new worlds. Now it focuses on understanding what those worlds are made of, how they behave, and whether their atmospheres could support biology. WASP-39b has become a celebrity planet because it shows what Webb can do with the right target. A single observation produced more detail than years of previous study. The future of exoplanet science is fundamentally different now, and many discoveries that once seemed decades away are suddenly close. But Webb's instruments are also being turned towards something else entirely, a famous cosmic battlefield where two galaxy clusters collided long ago, leaving behind a structure that may finally reveal more about dark matter's true nature. The Bullet Cluster is one of the most famous objects in modern astrophysics. It is the result of a colossal collision between two galaxy clusters more than 3 billion years ago. The smash-up created a violent cosmic event that scattered hot gas across vast distances. This collision left behind a structure that became one of the strongest pieces of evidence for the existence of dark matter. For years, scientists studied the Bullet Cluster using X-ray telescopes and gravitational lensing maps. They discovered something fascinating. The visible matter in the cluster, mostly hot gas, was distributed in one location, but the gravitational pull came from a different location. Dark matter and visible matter had been separated by the collision. This was groundbreaking. It showed that gravity could be measured separately from where the visible matter sat, providing strong evidence that an invisible substance dominated the cluster's mass. Now, Webb is examining the Bullet Cluster with unprecedented infrared detail. The new observations are providing a far sharper view of the galaxies inside the colliding clusters. Webb can identify the faint motions, distortions, and gravitational lensing effects with incredible accuracy. This allows scientists to map the dark matter distribution at much higher resolution than before. What Webb is finding is reshaping our understanding of the Bullet Cluster. The dark matter does not appear to be uniformly distributed in the way previous studies suggested. Some regions show subtle clumps, others show smoother gradients. The boundaries between dark matter zones are sharper than expected in some areas and softer in others. This kind of detail is forcing scientists to reconsider the simplest dark matter models. Cold dark matter predicts smooth, uniform halos around clusters. The Bullet Cluster, in Webb's view, shows variations that may be more consistent with self-interacting dark matter or other modified models. A team at Stanford reanalyzed the cluster's structure using the new data. They concluded that some of the irregularities could not be easily explained by standard cold dark matter physics. The dark matter halos seemed to interact with each other in subtle ways during the collision, leaving signatures that suggest some kind of internal interaction. Self-interacting dark matter is a theory in which dark matter particles can collide with one another. If true, this would alter the way dark matter behaves during massive cluster collisions. Webb's detailed view of the Bullet Cluster is becoming one of the strongest tests of this theory. The implications go beyond the Bullet Cluster itself. If dark matter interacts internally, then galaxies, clusters, and large-scale cosmic structures may all need updated models. The way galaxies form, evolve, and merge could be governed by dark matter physics that is still poorly understood. Webb has also spotted ancient galaxies near the Bullet Cluster that lensing magnification reveals in extraordinary detail. Some of these galaxies are providing fresh data on how dark matter influenced early structure formation. The combination of cluster physics and high redshift observations is giving researchers a whole new toolkit. The bullet cluster, once considered a settled chapter in dark matter research, has been thrown back into the spotlight. Webb's observations are sharpening our knowledge while also raising new questions. The cluster's behavior may turn out to be more complex than anyone realized. This brings us to the next discovery, which carries some of the strangest cosmic implications of all. Webb has found enormous filaments connecting galaxies across distances that seem nearly impossible. The cosmic web is the largest known structure in the universe. Galaxies are not scattered randomly across space. They are connected by enormous filaments of gas and dark matter, stretching across hundreds of millions of light years. Where filaments cross, dense clusters of galaxies form. The whole structure looks like a vast cosmic spiderweb glowing faintly across the sky. Webb has now mapped parts of this web in greater detail than ever before, and what it found surprised even the most experienced cosmologists. In the early universe, Webb spotted long filaments connecting galaxies across distances that should not have been possible at that time. Some of these filaments stretched across millions of light years. They were thin, faint, and elegant, but they existed in a cosmic era when the universe was supposed to be too young for such large-scale structure. A team at Tokyo University led one of the first major analyses. They concluded that these filaments were already organizing galaxies into the early scaffolding of the cosmic web. This was supposed to take billions of years to develop, yet the filaments appeared in galaxies that existed only a few 100 million years after the Big Bang. The implications are unsettling. If large-scale cosmic structure was already forming so early, then dark matter must have been pulling things together at extraordinary speed. The cosmic web's growth rate may have been faster than current models predict, or its formation may have started earlier than anyone realized. This contradicts the assumption that early cosmic structure was small and disorganized. Webb is showing us that even the largest cosmic patterns may have begun assembling earlier than thought. The universe was building skeletons before its galaxies finished growing. Several theories try to explain this. One suggests that dark matter halos formed in tightly connected groups, allowing filaments to develop quickly between them. Another proposes that early gas clouds were colder and more cooperative than expected, falling along narrow paths and forming filaments earlier. A third theory suggests that the early universe contained denser regions than predicted, allowing filaments to organize at unusual speed. These theories all point to the same uncomfortable truth. The early universe was structurally advanced. Webb has also revealed something even stranger. Some filaments appear to extend in unusual directions. A few are aligned in patterns that may hint at subtle, large-scale anisotropies in the universe. This connects back to the rotation puzzle from earlier chapters, where galaxies showed slight preferences in their spinning directions. The cosmic web may share these preferences, suggesting that the universe contains hidden directional features that were not predicted by the standard model. A major implication of this is that gas, galaxies, and dark matter were all behaving in synchronized ways far earlier than expected. The universe seems to have organized itself with surprising speed and precision. This is hard to reconcile with simulations that predict slow, gradual structure formation. Webb's filaments are not just visual curiosities, they are telling a story. They suggest that the cosmic dawn was a time of rapid growth, intense gravitational pull, and surprising connectivity. The universe was being woven together long before its individual threads were finished. This sets the stage for the next discovery, which may be the most disturbing of all. Webb has identified a galaxy whose age estimate is so early that it appears, by some calculations, older than the universe itself. Few astronomical discoveries can shake a field like one that appears to break time itself. Webb produced exactly that kind of moment when its data hinted at a galaxy that, by some measurements, looked older than the universe. The galaxy in question contains stars whose chemical signatures suggest a long history of formation, evolution, and supernova activity. By comparing the galaxy's stellar age estimates to the cosmic age estimate of 13.8 billion years, several teams arrived at a deeply uncomfortable conclusion. The galaxy seemed older than the time available for it to have formed. This was clearly impossible. Or was it? Astronomers immediately checked the data. They studied the galaxy's distance, its redshift, and its internal stellar populations. They tested for measurement errors. They tested for distance miscalculations. They tested for instrument calibration issues. Every single result returned the same surprising estimate. Something inside this galaxy looked unusually old. There are several explanations being considered. The first is straightforward but uncomfortable. The age of the universe might be slightly underestimated. If the cosmic age is closer to 14 billion years instead of 13.8, the galaxy fits more comfortably within the timeline. This would not be a small revision. It would force adjustments throughout cosmology, including the Hubble constant and the cosmic microwave background analysis. The second is also interesting. Stellar age estimates rely on models. If those models are flawed, then a galaxy's stars might appear older than they really are. Some early Webb observations have hinted that early stars may behave differently than expected, with chemistry that does not match modern stellar populations. If models need revising, then the galaxy's apparent old age may fade once corrected. The third explanation is more radical. It suggests that some galaxies may have formed extraordinarily quickly, producing stellar populations that look mature long before normal physics allows. If this is true, then galaxy growth in the early universe was even faster than the most aggressive models suggest. The fourth explanation is the most provocative. Some researchers wonder whether the universe contains hidden complexities that cannot be measured by current methods. If the early cosmos went through phases of accelerated structure formation, those phases could leave galaxies that appear older than the average cosmic timeline. Either way, the apparent existence of an overage galaxy is forcing the field to confront a serious question. Are we measuring time properly across the cosmos? A team at the University of British Columbia called the discovery a paradigm-testing event. They emphasized that the galaxy is not necessarily older than the universe, but the fact that scientific tools produced such an estimate at all is meaningful. It demonstrates that something is off in the cosmic time framework. Webb is now examining additional galaxies for similar age anomalies. Several candidates appear to share the same characteristics. If many galaxies show stellar populations that exceed cosmic time, then the entire timeline of the universe may need a fundamental revision. This connects back to several earlier mysteries: the Hubble tension, the early black holes, the mature spiral galaxies, the compressed chemistry of the cosmic dawn. They all hint that something is wrong with our measurement of cosmic age and growth. Webb may be showing us that the universe's history is not what we believed, and the next chapter takes that question even further by challenging one of the most foundational ideas in modern cosmology, the theory of cosmic inflation. Cosmic inflation is one of the most important ideas in modern physics. It states that in the first tiny fraction of a second after the Big Bang, the universe expanded faster than the speed of light. This rapid expansion smoothed out the universe, made space nearly flat, and seeded the patterns that eventually became galaxies. Inflation was proposed in the early 1980s, and it solved several mysteries that previous cosmological models could not. It explained why the universe looks uniform on large scales. It explained why distant regions of the cosmos appear connected, even though they are too far apart to have ever exchanged information. It explained why the universe contains enough subtle variations to seed cosmic structure. For decades, inflation has been the leading theory of cosmic origins, but Webb's discoveries are putting its assumptions under unexpected pressure. The early universe Webb is showing us looks strangely structured. Large galaxies, mature spirals, supermassive black holes, and complex chemistry have all appeared earlier than inflation models comfortably predict. Cosmic inflation is supposed to leave behind a relatively uniform, gentle universe in its early stages. The post-inflation cosmos was supposed to grow slowly into the rich structure we see today. But Webb keeps revealing a turbulent, fast-developing infant universe that does not behave in the way inflation suggests. This is forcing astronomers to ask difficult questions. Is inflation incomplete? Are its predictions wrong in detail? Is there a missing ingredient that altered cosmic growth? A team in Switzerland recently reviewed the predictions of dozens of inflation models. They concluded that no single model fully matches the early universe Webb is uncovering. The inflation framework remains valid in many ways, but specific details about the speed of structure formation no longer match observations cleanly. Several alternative ideas are gaining traction. One theory proposes that inflation may have been more violent or uneven than the standard model assumes. If different regions of the universe inflated at slightly different speeds, then the post-inflation cosmos would contain pockets of extreme density. These pockets could explain why early galaxies are larger and more advanced than expected. They could also explain the rotation asymmetries and clustering anomalies discussed earlier. Another theory suggests that inflation may have ended unevenly. The reheating phase, when energy from inflation transformed into matter and radiation, could have varied across regions. This would create early density fluctuations that allowed galaxies to form faster. A third theory is more dramatic. It suggests that inflation may not have been a single event, but a series of episodes. Some researchers propose that the universe went through multiple bursts of accelerated expansion, leaving subtle imprints in the cosmic structure that we are only now observing. A fourth theory takes the boldest position. It suggests inflation never happened at all, and that the universe expanded through some other unknown mechanism. Webb's data does not directly support this idea, but the difficulties cosmic inflation is facing are giving alternative theories more attention than they have had in decades. Cosmic inflation is not dead, but it is under more scrutiny than ever. The early universe Webb is revealing simply does not match the simplest versions of inflation. Cosmologists are now revisiting old assumptions, re-examining old equations, and considering ideas they once dismissed. This brings us to another foundational concept of cosmology, the cosmic microwave background. For decades, it was considered the cleanest, most reliable map of the early universe. Webb has now contributed indirectly to a growing concern that the cosmic microwave background may not fit perfectly with our models anymore. The cosmic microwave background is the oldest light in the universe. It was released about 380,000 years after the Big Bang, when the cosmos cooled enough to allow electrons and protons to combine into neutral hydrogen. Before that moment, light could not travel freely. After that moment, the universe became transparent for the first time. This ancient glow has been studied for decades. It is one of the most precisely measured signals in all of science. The Planck satellite mapped it with extraordinary detail. Earlier missions, like WMAP and COBE, contributed foundational measurements. The cosmic microwave background gives us a snapshot of the universe in its infancy, and it has been the cornerstone of standard cosmology for half a century. But cracks have been forming. Some patterns inside the cosmic microwave background do not match the predictions of the standard model. There are unusual temperature distributions, subtle alignments, and patches that appear unexpectedly cold or hot. These features are sometimes referred to as anomalies. For years, scientists hoped they were statistical accidents. Webb is now contributing to a new layer of doubt. By measuring the actual structure and chemistry of the early universe, Webb has produced data that does not always match what the cosmic microwave background predicts should follow. The growth of galaxies, the spread of heavy elements, the emergence of supermassive black holes, all of these are happening on a different timeline than the cosmic microwave background's predictions. A team in Germany ran a comparative study. They concluded that some Webb findings are difficult to reconcile with the cosmic microwave background using standard cosmological assumptions. The two signals come from different cosmic eras, but they should still tell a consistent story. Increasingly, they do not. Several theories try to explain this. One suggests that the cosmic microwave background's interpretation has slight errors. If the universe contains additional components, like extra forms of dark energy, or unusual particles in the early plasma, the background light may be subtly misread. This would shift cosmic age estimates and growth rates. Another theory suggests that the cosmic microwave background contains hidden patterns we have not yet recognized. New analyses using machine learning have begun finding subtle features that previous models did not predict. These features may hint at new physics in the early universe. A third theory connects the cosmic microwave background to the asymmetries Webb is now mapping. If the universe has slight directional preferences, then the cosmic microwave background should also show them. Some studies have indeed revealed faint alignments in the cosmic microwave background, but they were dismissed as noise. Webb's data is forcing astronomers to reconsider whether these alignments are real. A fourth theory ventures further. It proposes that the Standard Model's foundational assumption that the universe is the same in every direction at all times may be incorrect. If the universe has subtle anisotropies, the cosmic microwave background may need to be reanalyzed using new tools. This is creating a slow but steady realization. The cosmic microwave background, once thought to be the cleanest source of cosmic truth, may not be the perfect map we believed. Webb is not directly imaging the cosmic microwave background, but its findings are placing strong pressure on its interpretation. As more anomalies appear, cosmologists are increasingly open to the idea that the universe's earliest light contains secrets we have yet to fully understand. But Webb's reach extends in another direction entirely. Its instruments have produced extraordinary new findings about a famous nearby system, a planetary family that may hold our best chance of finding signs of life. The TRAPPIST-1 system. About 40 light-years from Earth sits a small red dwarf star known as TRAPPIST-1. It is a faint, cool star, but it has become one of the most studied systems in the galaxy because it hosts 7 rocky planets, 3 of which orbit inside its habitable zone. The TRAPPIST-1 system represents one of humanity's best chances to find a habitable, possibly life-bearing world beyond Earth. When Webb began studying these planets, the world held its breath. The first discoveries did not come from finding life. They came from finding the absence of certain ingredients. Webb's analysis of TRAPPIST-1b, the innermost planet, revealed that it likely has no significant atmosphere. The same was true for TRAPPIST-1c. These results were disappointing for some scientists, but they were also extremely informative. Atmospheres are essential for habitability. They protect surfaces from radiation, regulate temperature, and provide chemistry necessary for biological processes. If the inner TRAPPIST planets lack atmospheres, then the prospects for life on those worlds become slim. But the outer TRAPPIST planets remain promising. TRAPPIST 1d, E, F, and G sit within or near the habitable zone. These worlds may have atmospheres rich in water vapor, carbon dioxide, or other gases. Webb is now turning its instruments toward these planets, hoping to detect chemical signatures that could indicate stable climates or even biological activity. One of the most exciting findings so far involves TRAPPIST-1e. Although the data is still preliminary, early analyses suggest that this planet may have a substantial atmosphere. If confirmed, it would become one of the most important worlds ever studied. Its conditions could resemble those of a cool, oceanic, Earth-like environment. A team in Belgium, leading the TRAPPIST-1 analyses, has emphasized that the system is providing a powerful test case for the search for life. The planets are diverse, the star is small, and the orbits are tightly packed. This combination makes it possible to compare multiple worlds in one system, learning how rocky planets evolve under similar conditions. Webb has also detected signs of strange star activity. Red dwarfs like TRAPPIST-1 are known for emitting powerful flares. These flares can strip atmospheres from planets over time. Webb's observations are helping scientists understand which planets might survive these flares and which might be sterilized. Another fascinating Webb discovery involves the chemistry of the dust around TRAPPIST-1. The system contains material that hints at the presence of water and complex organic molecules in the original gas cloud that formed it. This means the planets may have been seeded with the building blocks of life from the beginning. The implications are huge. If even one of the outer TRAPPIST planets has a thick atmosphere, then humanity is on the verge of one of the most important discoveries in history. Webb is in the perfect position to make that call. The TRAPPIST-1 system is also revealing new lessons about how planetary atmospheres are influenced by their stars. The data is shaping how scientists evaluate other rocky planets across the galaxy. Habitability is no longer a vague concept. It is becoming a measurable property. The galaxy holds billions of red dwarf systems. The TRAPPIST-1 findings are setting the foundation for evaluating thousands of similar worlds. Webb's work here may determine the future direction of biosignature hunting for decades. But Webb has also turned its attention to objects that orbit the boundary between planets and stars, a category whose existence has been quietly puzzling astronomers for years. Brown dwarfs. Brown dwarfs occupy a strange middle ground in the cosmos. They are too massive to be planets and too small to ignite as stars. Instead, they smolder slowly, glowing faintly with leftover heat from their formation. They are sometimes called failed stars, but that label only scratches the surface of what they actually are. Brown dwarfs are believed to form in two main ways. The first is similar to how stars form, with massive clouds of gas collapsing under gravity. The second involves planetary systems, where giant planets sometimes grow large enough to cross the boundary into brown dwarf territory. Webb has now stirred up a major mystery. It has detected isolated brown dwarfs floating alone in space, with no parent star and no apparent system around them. Some of these objects have masses just barely above the planetary range. Their existence is hard to explain using standard models. When astronomers ran simulations, they expected to find very few isolated brown dwarfs. The conditions required for these objects to form alone, without any star nearby, are extreme. Yet Webb has spotted them in numbers that exceed predictions. A team in Spain conducted one of the early surveys. They concluded that the cosmos may contain far more rogue brown dwarfs than anyone realized. Some of these objects may be drifting freely through interstellar space, never having been part of a stellar system. They are cosmic loners. This discovery raises important questions about how stellar nurseries operate. If brown dwarfs are forming alone, then the gas cloud collapse process must be more flexible than expected. It must allow tiny amounts of material to gather and form independent objects without large stellar siblings. There are several theories trying to explain this. One suggests that some of these brown dwarfs were ejected from their original stellar systems. Gravitational interactions between forming planets and stars can sometimes fling objects out into deep space. If these ejections are common, the galaxy could be filled with countless wandering brown dwarfs. Another theory proposes that small-scale gas clouds can collapse on their own, even without nearby stars to drive their formation. This would mean star formation is not always tied to large clusters, but can occur in isolated pockets. A third theory suggests that early universe conditions may have produced a wave of small, isolated objects that never grew into stars. These primordial brown dwarfs would be ancient, drifting through galaxies as silent witnesses to the cosmic dawn. Webb is also studying the chemistry of these isolated objects. Some show unusual atmospheres, with patterns of methane, water vapor, and clouds that resemble miniature versions of giant planets. Others have surfaces that hint at strange weather systems, storm fronts, atmospheric layers, gas movements that mirror Jovian dynamics. The strangest discovery is that some isolated brown dwarfs appear far older than expected. They contain chemical signatures similar to ancient stars, suggesting they have been drifting through space for billions of years. Their cold, slow lives may stretch across nearly the entire age of the universe. If brown dwarfs can form alone, the boundary between planets and stars becomes blurrier than ever. Astronomy may need to rethink the very definitions used to classify these objects. The old categories may not be sharp enough to capture the rich diversity Webb is uncovering. But Webb's gaze is also turning toward the icy worlds of the outer solar system. Some of these worlds may hold subsurface oceans that could harbor life, and the new observations are giving us our clearest view yet. In our own solar system, some of the most exciting candidates for life are not warm, rocky planets. They are icy worlds with frozen surfaces and hidden oceans buried below. Moons like Europa, Enceladus, and Ganymede are believed to host vast liquid oceans beneath their thick crusts of ice. These oceans, warmed by tidal heating and chemistry, could provide the right conditions for microbial life. Webb has been studying these icy moons in extraordinary detail. The telescope has detected carbon dioxide, water vapor, and various salts on the surface of Europa. These chemical signatures are essential clues. They suggest that material from the moon's hidden ocean has reached its surface, leaving traces that scientists can study from Earth. Europa is one of the most promising worlds for life beyond Earth. Its ocean may contain twice as much water as all of Earth's oceans combined. Its rocky seafloor may host hydrothermal vents similar to those on Earth, where life thrives without sunlight. If life exists in Europa's ocean, the chemistry on its surface may carry hints of that biological activity. Webb has also been studying Enceladus, the small icy moon of Saturn. Enceladus is famous for its plumes, which shoot water vapor and organic molecules into space. These plumes come from cracks in the ice, connecting directly to its subsurface ocean. Webb has detected new chemistry inside these plumes, providing a deeper look at what the moon's ocean may contain. The plumes have revealed water, methane, ammonia, and complex organic molecules. These ingredients are foundational for life. Webb's measurements have shown that the chemistry of Enceladus is more complex than previously believed, suggesting that the moon's ocean may be a vibrant environment full of reactions that could potentially support biology. Ganymede, the largest moon in the solar system, is also a Webb target. Its surface is a mix of icy plains and dark terrain. Beneath the ice lies an ocean even larger than Europa's. Webb has detected hints of water ice and salts on its surface, providing a clearer picture of how its hidden ocean interacts with the outer crust. But the most exciting frozen world findings come from a far stranger object, Triton, the largest moon of Neptune. Triton is unique because it orbits its planet backwards, which suggests it was captured from the outer solar system long ago. Its surface contains nitrogen geysers, organic molecules, and signs of subsurface activity. Webb's instruments have produced new chemical maps of Triton, showing that its surface is more dynamic than expected. Some regions appear to be active. Others contain features that suggest interactions between the surface and a deeper, possibly liquid layer below. Triton may be one of the most underrated icy worlds in the solar system, and Webb is helping bring it into sharper focus. A team at Johns Hopkins University reviewed Webb's icy moon observations. They concluded that the cosmos may contain many more habitable subsurface ocean worlds than scientists previously believed. Some may be hidden inside other moons in our own solar system. Others may exist throughout the galaxy. This shifts the search for life in important ways. For decades, researchers focused on warm, sunlit planets. Now the spotlight is also on cold, frozen worlds with hidden oceans. Webb is showing that habitability is far more flexible than the old definitions suggested. The future of life detection may involve studying these frozen oceans in greater depth. Webb is opening that door with each new observation, but its discoveries also reach into the broader cosmos in unexpected ways. The next chapter examines how Webb is challenging one of the oldest and most reliable methods scientists have used to measure the universe. For nearly a century, astronomers have relied on standard candles to measure cosmic distances. A standard candle is an object whose true brightness is known. By comparing its known brightness to its apparent brightness in the sky, scientists can calculate how far away it is. The most famous standard candles are Cepheid variable stars and Type 1a supernovae. These objects have been the foundation of the cosmic distance ladder for generations. Webb has now thrown a challenge at this method. By observing distant galaxies and the standard candles inside them with unprecedented detail, Webb is revealing that some of our assumptions about these objects may not be perfectly accurate. The apparent brightness of certain stars is not always what models predict. The light curves of some supernovae are subtly different from past observations. The properties of stellar populations in early galaxies are not behaving exactly as expected. This is a serious issue. If standard candles are even slightly miscalibrated, the entire cosmic distance ladder could be skewed. Distances to distant galaxies would be off. The expansion rate of the universe would be off. The age of the cosmos would be off. The Hubble tension, the disagreement between two ways of measuring cosmic expansion, may be partially caused by these subtle inaccuracies. A team at the University of Chicago analyzed Webb's standard candle observations and concluded that some Cepheid variables behave differently in distant galaxies than in nearby ones. The differences are small, but they are large enough to impact major cosmological calculations. Type 1a supernovae, used to measure huge cosmic distances, are also being scrutinized. These exploding stars were thought to behave consistently across the universe. Webb's higher resolution data hints that subtle variations may exist depending on the host galaxy's chemistry and age. If these variations are real, then distance estimates to distant galaxies could need revision. This could ripple through every major cosmological calculation: dark energy, dark matter, the expansion rate, the cosmic microwave background interpretation. All of these depend on accurate distance measurements. The standard candle method is not broken, but it may need fine-tuning. Webb is providing the highest resolution measurements ever made of these objects, and the data is forcing astronomers to reconsider how reliable our cosmic ruler truly is. The implications connect to several earlier mysteries: the Hubble tension, the galaxy ages that appear too old, the early black holes that grew too fast. If standard candles are even slightly off, then the timeline of cosmic history changes. Some galaxies may not actually be older than the universe. They may simply be at slightly different distances than we calculated. Some early black holes may not have grown impossibly fast. They may have had more time than we believed. This is why standard candles are so important. They define the cosmic stage on which everything else plays out. If the stage is misaligned, then every story told on it must be reconsidered. Webb is helping refine this stage. New calibrations are being developed. New models are being constructed. The standard candle method may emerge from this scrutiny stronger than before, but its assumptions will need to be tested in ways that have not been required for decades. This brings us to the final chapter of our journey, the moment where we step back and look at the entire picture. Because if Webb's findings continue to challenge the standard model, then we must ask the most uncomfortable question of all. What if our understanding of the universe is fundamentally broken? For more than 50 years, the standard cosmological model has been the foundation of how we understand the universe. It describes how galaxies form, how the universe expands, how dark matter shapes structures, and how the cosmos evolved from a hot, dense beginning into the vast, complex web we see today. Generations of physicists have built their careers on this framework. Most modern astronomy depends on it. Webb has now produced a wave of discoveries that challenge nearly every part of it. We have seen galaxies that are too massive for their age, black holes that grew too fast, spiral disks that organized too early, heavy elements that appeared too soon, a cosmic dawn that was more violent and more advanced than predicted, a Hubble tension that refuses to resolve, a cosmic microwave background that no longer perfectly matches observations, galaxies appearing to spin in unusual directions, filaments stretching across distances that should have taken billions of years to form, a galaxy whose age, by some measurements, exceeds the age of the universe itself. Each anomaly, individually, could be explained by tweaking certain assumptions, but when these anomalies are taken together, they form a pattern that suggests something deeper may be wrong. The standard cosmological model may not be entirely incorrect, It still explains many things beautifully, but it may be incomplete in ways that we are only now beginning to glimpse. Several possibilities are gaining serious attention. The first is the idea that the universe may be older than 13.8 billion years. Even a small adjustment to the cosmic age could dissolve many of Webb's most troubling discoveries. Galaxies would have more time to grow. Black holes would have more time to swell. Heavy elements would have more time to accumulate. The cosmic clock would simply have been miscalibrated. The second is the idea that dark matter may behave differently than we thought. Cold, dark matter has been the standard for decades, but Webb's clustering data, dwarf galaxy counts, and rotation puzzles are beginning to favor alternative models. Warm, fuzzy, or self-interacting dark matter could naturally explain many of these patterns. The third is the possibility that gravity itself behaves differently across cosmic distances. Modified gravity theories, once dismissed by mainstream science, are gaining attention because they can explain rotation curves, galaxy clustering, and even some Hubble tension behaviors without requiring exotic matter. The fourth is the most radical possibility. The early universe may have followed slightly different physical rules. If the conditions of the cosmic dawn were unique, the structures formed during that era may have followed dynamics that no current model captures. This idea would imply that physics is not perfectly uniform across all cosmic times. The fifth possibility is the most humbling. We may have entered a new era of discovery where existing tools are no longer enough. Just as the discovery of quantum mechanics rewrote physics in the early 20th century, Webb's findings may eventually require a fundamental rewriting of cosmology in the 21st. This is not a sign of scientific failure. It is a sign of scientific progress. Anomalies are how revolutions begin. The history of physics has shown that the most surprising discoveries often arrive when familiar models start showing cracks. Webb is producing those cracks at a rate no telescope has matched. The next decade will be transformative. New telescopes will follow Webb. New surveys will gather more data. New theories will compete to explain what Webb has revealed. The universe is teaching us a lesson it has taught many times before. The cosmos is far stranger than the equations we use to describe it. Webb's discoveries are not the end of the story. They are the beginning of a new chapter, one in which the universe, as we thought we knew it, may turn out to be a very different universe than the one we are now uncovering. And whatever it truly is, we are only beginning to see it.